Next example has to do with something actually would be considered maybe in biology or in medicine.
I can't wait.
Oh, I'm glad. But it has to do with epidemics. If you consider the spread of a disease in a disease-free population, the model in example 1, 2, 3, and 4 would apply. That is, the number of sick people is some proportion of the people in the population, the number of people that get sick. In reality, with finite populations, eventually coming into contact with new people will involve some contact with people who are already diseased. So the model in example 1 is not accurate as this one is. That's to say the number of new cases is proportional to the product of the number of people who are diseased and the number of people who have not yet been exposed to the disease. And call the number of diseased X and the number not yet exposed Y, then the model is the change in the amount of diseased people is proportional to the product of the amount that have been exposed, that have the disease times the number that have not yet been exposed. If we further suppose that one infected person is introduced into a population of n disease-free people, then x plus y equals n plus 1. That's 1 is the extra person added. And solving for y, we get y equals n plus 1 minus x. And the equation is now the change in the number of diseased people is proportional to x, that's the number of diseased people, times n plus 1 minus x, which is what y is equal to, and that would be the number not yet exposed. That's the total number of the population, subtracting the ones that are diseased. And that is a first order nonlinear differential equation, and again I think this one might be a Bernoulli equation, and in the last lesson of this unit we'll learn how to solve those.
I agree.
I'm glad.